Welcome to the 12th week of live interactive session on the course Integral Transforms and their applications. So this is the last week of the live interactive sessions, and I think the course is going to end soon. So and exams are coming, so I hope you all prepared well. So today I will be going through the last session that we have, which is about the wavelet transform. I'll be solving some sample problems, and also we'll revisit the earlier transforms, especially the Fourier transform, which is much more important when we are doing wavelet transforms. So I hope this will give a clear idea of the previous transforms as well as the last one, which is the wavelet transforms. So if you have any questions, please stop me. So we'll move to the first problem. For the Haar wavelet, which is given by psi of x is 1 from 0 to half, minus 1 from half to 1, and 0 otherwise. Find its basically we have to find the discretized version of the Haar wavelet, which is psi of 2 raised to mx minus n for m and n being integers. Then its Fourier transform, then take its magnitude modulus. So that's what asked in the question. So you can try for yourself. So I may give 1 or 2 minutes for you to try this, and then I will explain how to do this. So meanwhile, let me remind you what is Fourier transform. So the Fourier transform of a function f of x to the frequency k is given as minus infinity to plus infinity integral e raised to minus I omega. Okay, let me write the frequency being omega. So it is minus I omega x f of x dx. And here the Haar wavelet, which if I draw, so from 0 to half its value is 1, from half to 1 its value is minus 1, then 0 everywhere else. So this is the form of a Haar wavelet. So what we are asked here is, first we have to so the discretized version of the Haar wavelet, which is psi of m comma n, which is given as psi of a0 raised to m x minus n. Okay, here specifically we have took the case of the factorization parameter being 2 and 1s, or a half and 1, so it is 2 raised to m x minus n. So this is the discretized version of the Haar wavelet, psi mn. So now we have to evaluate its Fourier transform, which is basically psi of 2 raised to mx minus n. So here remember that m comma n are integers. Okay, so this we are multiplying with e raised to minus I omega x dx integral minus infinity to plus infinity. Now we do a substitution. So 2 raised to mx minus n equal to t. Let me call this as expression 1. So from this we will get 2 raised to m times dx is dt. So that from now we substitute that back into expression 1, we will get the Fourier transform of psi mn. So see the limit, earlier it was for x, now it is for t. Even though we done the substitution, that is not going to alter the limits. Basically for the variable t, also the limit will be from minus infinity to plus infinity. So it is psi of t e raised to minus I omega x. So x will be now modified as n plus t divided by 2 raised to m. times dx, which is dt by 2 raised to m. So we'll take the constants outside. Basically 1 by 2 raised to m is a constant. Also if you see the exponential term, there e raised to minus I omega n by 2 raised to m, which is a constant. The remaining function of t, which is basically psi of t, and e raised to minus I omega t by 2 raised to m, they will be inside the integral. Now recall the definition of psi of x or psi of t. So from 0 to half, for the variable, its value will be 1, and from half to 1 its value will be minus 1. So basically what we will do is that we'll split the integral, and 0 everywhere else, so we'll just do 1 by 2 raised to m e raised to minus I omega n by 2 raised to m. Then basically 0 to 1, the psi of t is 1 times e raised to minus I omega t by 2 raised to m dt. We are splitting the integrals. Then 0 to half, 0 to half, then half to 1, its value is minus 1 times e raised to minus I omega t by 2 raised to m dt. Okay, and 0 everywhere else, so those parts I am not writing. So it is 2 raised to minus m e raised to minus I omega n 2 raised to minus m. Now this integral we can perform easily. It's e raised to minus I omega, just an integral of exponential, e raised to minus I omega t 2 raised to minus m divided by minus I omega 2 raised to minus m, where the limits for t is from 0 to half. And the next integral same, it's e raised to minus I omega t 2 raised to minus m by I omega 2 raised to minus m. Limits for t is from half to 1. Now we just need to take the constant outside, which is 2 raised to minus m e raised to minus I omega n 2 raised to minus m, then minus I omega 2 raised to minus m. So this is a constant. I can see this 2 will cancel. The remaining we will apply the limits, e raised to minus I omega 2 raised to minus m by 2 minus 1, and minus e raised to minus I omega 2 raised to minus m plus e raised to minus I omega 2 raised to minus m by 2. So this last term is actually identical to the first term, so they will add together, become 2 times. So now this quantity we can write as basically I by omega e raised to minus I omega n 2 raised to minus m. Then whatever inside the bracket, if you see, it's actually e raised to minus I omega 2 raised to minus m by 2 minus 1 the whole square with a minus sign. So that we can write here like e raised to minus I omega 2 raised to minus m by 2 minus 1 the whole square. Now here e raised to minus I omega and 2 raised to minus m. So this term we will modify it little bit, like e raised to I omega 2 raised to minus m by 2, or let's say this is minus 4, then minus e raised to minus I omega 2 raised to minus m by 4 times e raised to, okay, this is plus minus I omega 2 raised to minus m by 4. Now you can see this term the whole square. Basically what I am saying is that the term inside the bracket can be split into these 2 parts, product of 2 exponentials. So why I wrote like this is that now that this term can be like, if you remember, it's e raised to I theta minus e raised to minus I theta by 2y or this difference of the exponentials is 2i sine theta. So we'll use this equation here. So it's minus I by omega e raised to minus I omega n 2 raised to minus m. Now you see the square of this exponential we can take outside, and it's e raised to minus I omega 2 raised to minus m by 2. The remaining part is 2i sine of I omega 2 raised to minus m by 4, the minus m, the whole square. So this we can finally simplify to so there is an I square which is minus 1, that will make it plus. So it's I 4i by omega e raised to minus I omega n by 2 raised to n e raised to minus I omega by 2 raised to m plus 1 into sine square of sorry, there is not I inside the sine. Okay, sine square omega by 4 into 2 raised to n. So this is basically the Fourier transform f cap of omega. Now what is asked in the question is that you have to find its absolute value. So f cap of omega absolute value. So you can see here the I and exponential of I theta. So those things have absolute value which is 1. Sine square is just positive number, so sine square of omega by 4 into 2 raised to n. So this is the answer. So is this clear? Any question in this? So basically what we are doing is that the Haar wavelet is given, its expression, it's a continuous form. We are converting that to a discretized version, and we are asked to evaluate its Fourier transform. So that we are using the basic definition of the Fourier transform, and because a function in the discretized form has some variables which are like multiplication and translation, so we are scaling those factors out basically by substitution. 2 raised to m into x minus n, we are substituting as t. Even without substitution also we can do, but we have to take care of the limits, so that's why we did the substitution, so it is automatically taking care of the limits of the function. Now inside the integral psi of t only appears. For that the relevant interval is from 0 to half and half to 1, where the function's value will be non-zero, 1 and minus 1 respectively. Outside the intervals its value will be 0. So the integral needs to perform only on those intervals. We are taking out all the constants and only keeping the exponential terms which are dependent on the time, and then we are integrating. So then a little algebra we are just modifying a little bit. So finally we found the Fourier transform, and we are taking its absolute value, which is just a real number. So that's what we have done. So I hope that is clear. So we'll move to the next problem. The Gabor window function is defined by f of t is 4th root of 2a by pi times exponential of minus 8 square. So again we are asked to evaluate its Fourier transform. So this is basically a Gaussian function. Okay, so it's called Gabor window function. It's a wavelet. So if you plot the function, so see it's symmetric about 0, unlike the Haar wavelet which is symmetric about half, t equal to half. Okay, so here the function is symmetric about 0, so you'll see it's basically a Gaussian. Maybe I have drawn it non-symmetrically, but it should be a symmetric Gaussian function. Okay, so with the scale which is scaled with 4th root of 2a by pi. So this is psi of here it's actually f of t. So we are asked to evaluate the Fourier transform. Actually we have done the same things. Let me repeat the process again. It may remind you the old Fourier transforms and the techniques that we have used. So f cap of omega is minus infinity to plus infinity. So 2a by pi the whole raised to 1 by 4 exponential of minus at square exponential of minus I omega t dt. Take the constants outside, which is basically 2a by pi the whole raised to 1 by 4. Then integral minus infinity to plus infinity e raised to minus at square minus I omega t dt. So again 2a by pi the whole raised to 1 by 4. So we'll group the exponential in a way that, so we'll take the a outside and t square plus I omega by a times t. So we actually need to complete the squares, that is t square plus I omega by a t. Can we actually, so let me call this expression. So in that t square plus I omega t by a can be written using a completing square technique, like t plus I omega by 2a the whole square minus I omega by 2a the whole square. So I guess that is obvious that you can understand this is indeed the form of completing squares. Okay, so then which actually we can write as t plus I omega by 2a the whole square minus not minus, it's plus omega square by 4a square. So we substitute that back in equation 1. We will get f cap of omega as 2a by pi the whole raised to 1 by 4 integral minus infinity to plus infinity e raised to minus a times this expression. So that is t plus I omega by 2a the whole square, again minus a omega square by 4a square, then dt. Now we take the constant again outside. We have an exponential constants appearing, which is e raised to minus omega square by 4a. So we take an outside. Now integral minus infinity to plus infinity e raised to minus a t plus I omega by 2a the whole square dt. Now remember this expression e raised to minus ax square dx minus infinity to plus infinity will be square root of pi by a. So the standard result we are going to use here, so that this integral will have an expression of root pi by a. So it's basically 2a by pi the whole raised to 1 by 4, then square root of pi by a exponential of minus omega square by 4, which is the Fourier transform of the Gerber-Window function. See, that is also a Gaussian. So if you plot it's a Fourier transform. This is also a Gaussian function. With respect to omega, with the appropriate scale, that's all. So you can actually write this in terms of f itself, because the f is given as 2a by pi the whole raised to by 4 exponential of minus 8 square. So if t is omega by 2a, so that is f of omega by 2a, which is with the scaling parameter root of pi by a, you will get the same answer. So that's basically the relation between just the fact that we have the function Gerber-Window function, which is Gaussian kind. We still have its Fourier transform being another Gaussian, and they are related. So it's basically the wavelet is actually scaled, not shifted, but scaled version of the same function. So I hope that is clear. Any questions in this? Okay, if not, we will move to the next question. So find the Fourier transform of the piecewise linear spline wavelet. So its equation is given. Psi is 1 minus absolute of t minus 1. For t is from 0 to, okay, that's a mistake, actually it is 0 to 2 and 0 otherwise. So you have to evaluate its Fourier transform, but before that I suggest all of you to draw how the function look like, basically the wavelet, how it look like, then evaluate its Fourier transform. Basically linear like the function is linear but piecewise linear, that's why we call it piecewise linear. Then it is a spline wavelet, so it's actually a spline of degree 2. So you draw the wavelet, how it look like, and then evaluate its Fourier transform. So I may give you some time for this, then I will show how to do this. Okay. So I hope this is easier for you to do, like, because the the piecewise linear spline, so you can actually, now it is a piecewise function, but still you can split it again. When t is from 0 to 1, the mode t minus 1 will become 1 minus t. For 0 less than t less than 1. Now 1 to 2, it will be t minus 1. So using that fact, you will find it is t for 0 to 1, basically psi of t I am saying. Then 2 minus t for 1 to 2. Then 0 otherwise. So if you draw the function, the wavelet will look like this. It's a linear with from 0 to 1, a triangular kind of shape. So 0 to 1 and 1 to 2, it's a slope with the minus 45, value being 1 here, so it's a psi of t, maximum value. Okay, and 0 everywhere else. So this is the linear spline wavelet. So now we have to evaluate its Fourier transform. So again, using the basic definition, we'll start the Fourier transform. Is integral minus infinity to plus infinity e raised to minus I omega t psi of t dt. So it's a psi of t has like two function in definitions in the limit 0 to 1 and 1 to 2 and 0 everywhere else. So basically we have to integrate from 0 to 1 with the t and e raised to minus I omega t. Then 1 to 2 it's like 2 minus t, then e raised to minus I omega t dt. That's all, and 0 everywhere else. So now before doing this expression, okay, we can split it again, 0 to 1, then 1 to 2 by integral. Subtraction is acting on t e raised to minus I omega t dt, then plus 2 times 1 to 2 e raised to minus I omega t dt. Let me call this expression 1. So integral of exponential is easy, but t times exponential is a little complicated. Not little complicated, it's actually easier, but we have to just evaluate it. So how will you do that? I mean, we can use the integration by parts, as the first function being t, second function being e raised to at. So it's a u into integral of the v minus derivative of u and integral of v, which is then double derivative of the first function, because we have t as the first function, so double derivative is 0, so the remaining terms will be 0. So this is the integral with the integration constant that we don't need to give when we are applying the limits. So which we will substitute in equation 1. What we will find is that 0 to, okay, we have to apply t e raised to minus I omega t by minus I omega, then minus e raised to minus I omega t by minus I omega the whole square, which is I omega the whole square, which is minus omega square. So this we have to apply a limit 0 to 1, then subtract the same function but limit is now from 1 to 2, plus the last integral, which is 2 into e raised to minus I omega t by minus I omega, limit from 1 to 2. Now we gradually apply the limits. So all these limits are applying for the variable t. So first 1 e raised to minus I omega by minus I omega plus e raised to minus I omega by omega square minus the value at 0, which is 0 minus 1 by omega square. So we'll just write minus 1 by omega square here. Then minus now the function's value at 2, t equal to 2, which is 2 e raised to minus 2i omega by minus I omega plus e raised to minus 2i omega by omega square, then plus e raised to minus I omega by minus I omega plus e raised to minus I omega by omega square plus 2 e raised to minus I omega by minus I omega minus 2 e raised to, okay, this 2 was here, and then okay, 2 e raised to minus I omega by minus I omega. Now we take this bracket open by bringing the minus inside. So now we can see, okay, this minus will get cancelled with this and this become plus, and this minus we can bring in front. This minus also we can bring in front of the function. Again this minus, and this minus will cancel with this minus, become plus. Now if you see this term along with this term will become minus 2 times e raised to minus I omega by I omega, which we can cancel with the last term, which is plus the same quantity. So basically they will cancel. Then so here is another term, which is 2 e raised to minus 2 omega by I omega, and here is the negative of the same term, so they will cancel. So the remaining terms, if you see, it's this term and this term will add together, 2 e raised to minus I omega by omega square. Then this term will be minus 1 by omega square, and this term, which is minus e raised to minus 2 I omega by omega square. So we group the omega 1 by omega square term outside, like 1 by omega square, then also take a minus outside, so 1 plus e raised to minus 2 I omega minus 2 e raised to minus I omega. Now you can see this is basically minus 1 by omega square times 1 minus e raised to minus I omega the whole square. Okay, so again like we have done earlier, we will split the 1 minus e raised to minus I omega term, like e raised to I omega to minus e raised to minus I omega by 2, multiplying with e raised to minus I omega by 2, then taking the entire square. Okay, so which we will write as 1 minus 1 by omega square e raised to minus I omega, and the remaining term is 2y times sine of omega by 2 the whole square. So which will become 4 by omega square e raised to minus I omega sine square omega by 2. So is that clear? So basically we are evaluating the Fourier transform of the piecewise linear spline wavelet, which we can basically, if you plot, it will look like triangular pulse. So then we are evaluating its a Fourier transform, so we will get something like this, and it's basically a sine square function with 1 by omega square. So this is its Fourier transform psi cap of omega. So if you are checking the admissibility condition, I mean, you can check this for the earlier cases as well. And of course we know for the Haar wavelet it is not like the decay rate is not that good. So basically C psi is like infinite because the decay is like 1 by omega only. But here you can check psi cap of omega, the mod by omega d omega minus infinity to plus infinity. It has an omega square, okay, absolute square, so which will be minus infinity to plus infinity, 16 by omega raised to 5, and sine raised to 4 omega by 2, which is of course less than infinity because sine is a bounded function, but 1 by omega will like decay as 1 by omega raised to 5. So the integral is converging fast, so this is a nice function in that sense compared to the Haar wavelet. Okay, so any question? So if not, we will move to the next one. So find the Fourier transform of the Mexican hat wavelet. So again, I will give you some time for do this yourself. So first plot the function and see how the wavelet look like, then evaluate its Fourier transform. So a hint is that actually this is like a polynomial times an exponential, polynomial times a Gaussian. So this particular function, which is the Mexican hat, has a property which is basically second derivative of the Gaussian itself related to. So you can actually use the properties of Fourier transform to perform this, or you can do the entire calculus, but it will take some time. So that's why use a property, it will be better. So I'll wait for a moment. So if you have watched the lecture videos, it's already mentioned about the Mexican hat wavelet there. So let me plot how it will look like. So it's basically the exponential or Gaussian function multiplied with the polynomial, which is 1 minus t square. So it should vanish at t equal to 1 and vanish at infinity and minus infinity like a Gaussian with some moment t square multiplied. So and is at t equal to 0, its value is 1. So you can see it to look something like this. And symmetrically the other side also. Maybe I will draw asymmetrically, but assume that is symmetric. Okay. And it will resemble Mexican hat, that's why. So its value at so here it is t and here it is psi of t. So value at t equal to 0 is 1. And when t is 1, it is 0. And and decays to exponentially or like a Gaussian in the infinity. So we need to evaluate its Fourier transform. So psi cap of omega, basically you can see it's the Fourier transform of minus the Fourier transform of d square by dt square of exponential of minus t square over 2. So when like using the properties, now you can write it's a minus I omega the whole square times just the Fourier transform of exponential of minus t square over 2. So the Fourier transform of the Gaussian exponential of minus t square over 2 will also be a Gaussian. So if you don't remember that, we can do that at least, like the Fourier transform of exponential of minus t square, let's say a t square more generally. And for us a is just half, that we'll substitute later. Let me call this as expression 1 now, which is e raised to minus a t square e raised to minus I omega t dt integral minus infinity to plus infinity. And little earlier we have showed how it will look like, just square root of pi by a times exponential of minus omega square by 4a. So in 1 we put a equal to half. So we will get, okay, let me call this as 2. So substitute a equal to half in 2. Then expression 1 gives psi cap of omega basically minus I omega the whole square is minus omega square is plus omega square times square root of pi by a times exponential of minus omega square by 4 times a was actually half, so it will come here and this will become half. So it's square root of 2 pi omega square e raised to minus omega square by 2. This is its Fourier transform. Now this is also a polynomial multiplied with Gaussian with some scaling. So if you try to plot its Fourier transform, they should go to 0 at omega equal to 0, and at infinity also it decays, but initially it has a growth because it's a quadratic multiplication. So you will see it's a quadratic growth initially, but reaches a maximum because of the exponential, it will again further decays. Similarly, symmetrically, you can find in this on the left side also, like a quadratic growth, then reaches a maximum, then decreases. Okay, I have drawn it symmetrically, but It's actually a symmetric function. Okay. So this is the Fourier transform of the Mexican height function with omega plotted. So any question in this? Okay, so if nothing, we will move to the next question. So find the Fourier transform of the Wavelet wavelet, which is given by exponential of I omega 0 t minus t square over 2. So unlike the earlier wavelets, you can see Wavelet wavelet is, it's a Gaussian with an exponential or oscillatory part multiplied with it. It's actually e raised to minus t square over 2 multiplied with e raised to I omega 0 t. It has both real and imaginary part. So the Wavelet wavelet has the real part being cos omega 0 t times e raised to minus t square over 2, which is the real part of Wavelet wavelet, and the imaginary part of the Wavelet wavelet is sine of omega 0 t times exponential of minus t square over 2. So I suggest you to plot this Wavelet wavelet in the complex space and then evaluate its Fourier transform. So I may give some time for you to do that, then I will show how to do this. Have you plotted the Wavelet wavelet? So like I said, it has both the real and imaginary part. So we can first plot just real component. So with the time, so it's actually a Gaussian multiplied with a cosine function with some frequency. So assume some omega 0, and what we will see is that, like cos function, it will have a peak at the middle, then it will have other frequencies but exponentially damped versions, symmetrically the other side also. Should be symmetrical. Okay. So this is the real part of the moral wavelet. And now the imaginary part, it is actually a sine function multiplied with the exponential or Gaussian. So you will see like a sine function, it will be going 0 and a linear when t is very small, then it will go to maximum value. Then because of the Gaussian multiplication, it will decay, and symmetrically other side, but it's like an anti-symmetrical, like because the sine function is anti-symmetric function, so like that we will get. So probably frequencies are not matching, but you should remember that both have plotted with the same frequency omega 0, so it would actually match, but yeah, when I plotted it didn't match. So okay, so I hope that it is not going to make an ambiguity, so it's just my plotting mistake. Psi I of t. Now actually you can combine these two. Now we have plotted this in 2D space, that's why it's actually looking like this, but I can combine this in a 3D plot. Actually it should look like so like a spiral, spiral with amplitude being decaying, like let me try to plot this. I don't know how well it will come, so it should be something like this. Basically we're combining the sine and cosine, so in the 3D space it should look like something like this. Okay, so in this direction we have the time axis, then the psi real and psi imaginary, so everything plotted look like this in the 3D scale. So it has both oscillations in the real direction and as well as the imaginary direction, so that's why it is like spiral in the 3D space. So now we have to take its Fourier transform. So the Fourier transform is just by definition it's minus infinity to plus infinity. First the function, which is e raised to I omega 0 t, e raised to I omega 0 t minus t square over 2, then exponential of minus I omega t dt. See, omega 0 is the intrinsic frequency of the Morley wavelet, but we are using an outside frequency to evaluate this Fourier transform, which is omega. Now we group every term in exponentials, like a into omega 0 minus omega minus t square over 2 dt. So we can write as minus infinity plus infinity, e raised to minus half t square minus I times omega 0 minus omega dt. So like we have done earlier, this we can complete the squares, so it will be raised to minus half t minus I into omega 0 minus omega by 2 the whole square, which is now minus or plus omega 0 minus omega by 2 the whole square. Okay, made a mistake, should be 2 here, so that is making this is 1 and this is also 1. Now we can take the constants outside, which is minus half omega 0 minus omega the whole square times the integral minus infinity to plus infinity, okay, e raised to minus half t minus I omega 0 minus omega the whole square. So this is an exponential integral, so Gaussian integral, so basically root of 2 pi should be the answer, because the factor is a is 1 by 2, so that will make the answer to be square root of 2 pi. So we'll get the answer being square root of 2 pi times exponential of minus half omega 0 minus omega the whole square. Yeah, or because the square you can also write as omega minus omega 0 the whole square. Both are same. So that's the solution. So any question in this? So see, actually the Fourier transform is a real quantity. Now what we will see is that it's just a Gaussian. So if you plot the Fourier transform of the Morley wavelet, it is just shifted Gaussian actually, with omega 0 being the intrinsic frequency, shifted scaled to also square root of 2 pi. But we will see it's basically a shifted Gaussian. Oh, it should be other side. Okay, yeah. At the location omega 0, we will see it's shifted to that location. So that is what f prime of omega or psi cap with omega. So this also you can find, this also has the admissibility criteria it obeys, because this also decays faster than like 1 by omega, unlike a R wavelet. Okay. So any questions? Okay, so if no questions, we may end today's session, and this is our final session, and so I hope you all have well prepared for the exam. So we have the topics, if you remember, we have basically a lot of transforms, the Fourier transform, then we had seen the Laplace transform, Mellin transform, then Wavelet transform that we have seen now, then the Fourier transform in the polar coordinates, which is known as the Hankel transform, then discretized version of the transform, which is the Z transform. So basically to solve difference equations, unlike the other transforms which are continuous transforms. And in the last class we also seen that is not a transform, but okay, before the last class we also seen a transform which is the basically evaluating the projection. I forgot its name, but that transform is there. And then in the last class we have seen it's not transforms, but we have used many transforms, especially the Laplace transforms, to evaluate the fractional derivatives and fractional differential equations. So these are the topics. I think I have missed some more, but yeah, main topics. And so you have to go through all of this and prepare well. So good luck for your exams. Okay, so any questions? Okay, if nothing, we'll stop here for today. Okay.